this stuff already. Section 5.1 is simplifying, and Section 5.2 is verifying. I just want to review a few things with you. These Pythagorean identities are very helpful, and remember that you can manipulate them. So for example, I could subtract sine squared from both sides, and then my result would be cosine squared theta is equal to 1 minus sine squared theta. So if I ever saw 1 minus sine squared theta in a problem, I could replace it with a cosine squared theta. Same thing goes with all of those. For example, here we could subtract 1 from both sides, and then tangent squared theta would equal secant squared theta minus 1. The cofunction identities are also very helpful. Remember, these were when the angles are complementary. When the angles are complementary, then the cofunctions are equal. So remember, like if I have an angle and I want to find its complementary angle, I would subtract from 90. Same thing goes with radians, but it would be pi over 2. So that's why all of these are like the pi over 2 minus u versus u. Those would be complementary angles. And then the cofunctions are sine and cosine, secant and cosecant, tangent and cotangent. So basically, whenever you see the pi over 2 minus u or pi over 2 minus theta, that should make you remember cofunction identities. Other helpful tips: factor things if you can. If you can factor something out, you might notice difference of squares or factoring like a quadratic. If you are adding or subtracting two fractions, make sure you get a common denominator. Multiplying by a conjugate might help. So this is like what we did when we had complex numbers. Do you remember how, like, if I had, let's say, 2 plus I in the denominator, remember how we would multiply by 2 minus I, the conjugate? We might use that same idea, but with trig. If you are really getting stuck, changing things into sine or cosine might help. And if you are verifying, only work on one side. Don't move anything across the equal. And only work on one side. Don't work on both sides. Okay, so keep these things in mind as we do our examples. All right. Our first example here, you will notice that this right here, hopefully you'll recognize, is one of the Pythagorean identities. And remember, those can get manipulated. So the first Pythagorean identity is sine squared theta plus cosine squared theta equals 1. If I want to have a 1 minus cosine squared, I can just subtract the cosine squared from both sides. So that means that sine squared theta is equal to 1 minus cosine squared theta. So wherever I see this 1 minus cosine squared theta, I can replace it with a sine squared theta. And that's times cosecant theta. Now, cosecant we know is 1 over sine, so that might be helpful to change it. And since I'm multiplying, I could combine them into a single fraction. And I have 2 sines on the top and only 1 sine on the bottom. So I can cancel 1 from the top and 1 from the bottom, and I'll just be left with a sine theta. And that looks very simplified, so we would be done. In this example, when you see the pi over 2 minus x, remember those were cofunctions. All right, so sine, the cofunction of sine is cosine, and the cofunction of cosine is sine. And when we divide those, we get cotangent. And that looks simplified. This one, basically anytime I see a trig function squared along with a 1, I think of the Pythagorean identities. And the Pythagorean identity that deals with secant squared looks like this. It's tangent squared theta plus 1 equals secant squared theta. So if I subtract the 1 from both sides, tangent squared theta equals secant squared theta minus 1, which is what I have over here. So therefore, this is tangent squared x. I'm multiplying that by cosine squared x. So now what we ask ourselves is, can we change either of those? Well, if you get stuck, remember I said turning things into sines and cosines might be helpful. So tangent squared I could write as sine squared x over cosine squared x. And I still have this cosine squared x in front. And now you might notice, oh, those cosine squareds would cancel. And I would be left with a sine squared x. And that looks simplified. This one, the top does look like a Pythagorean identity. The Pythagorean identity that deals with cosecant squared looks like this. It's cotangent squared theta plus 1 equals cosecant squared theta. So yes, I could subtract 1 from both sides. And I could say that cosecant squared theta minus 1 is cotangent squared theta. All right, now, but here's the problem. Do you see the bottom does not have a squared? So I can't use Pythagorean identity on the bottom. Also, from the very beginning, nothing would have canceled because I'm not multiplying on top and bottom. So I get to here, and I kind of get stuck. So I would say, let's try a different approach then. So I'm going to rewrite the problem. And when I'm looking at the top, I see two terms with a minus sign. And both of those terms are perfect squares. So I'm going to approach this as a difference of squares. And I'm going to factor the top. So this is just being kind of sneaky. So if I factor the top, and I'm using my difference of squares, I remember that one will be a plus and one will be a minus. So I need two identical things that make a cosecant squared theta. So that would be a cosecant theta and another cosecant theta, because those would make a cosecant squared theta. And then I need two identical things that will make a 1. So that would be a 1 and a negative 1. Well, they have to make a negative 1. Now on the bottom, I have cosecant theta minus 1. Now do you see what cancels? The cosecant theta minus 1s will cancel, and I'll just be left with a cosecant theta plus 1. And that's about as simple as it's going to get. So the bottom line is, if you feel like you get stuck, try a different approach. Sometimes this factoring or the difference of squares idea might work a little bit better. Okay, in that spirit of factoring, keep that kind of in the background. That factoring might be actually very helpful. So in this problem, I have two terms, and both of those terms have a sine x. So it might be helpful if we factor out a sine x. What would we be left with? Well, this first term right here, if I take out a sine x, I'd be left with a cosine squared x minus. And if I take out a sine x here, I'm left with a 1. If it helps you to think about distributing back through, we would get back to where we started. Now, the stuff in the parentheses, hopefully you recognize that is one of those Pythagorean identities, just rearranged. So maybe I'll work up here. Sine squared x plus cosine squared x equals 1. That's the first Pythagorean identity. I want it to be a cosine squared minus 1. So I'm not going to subtract cosine, because if I subtract cosine, I'll just show you. If I subtract cosine squared x, that would be 1 minus cosine squared x, and that's not the same. So I don't want to do that. I'm going to erase what I had. Okay. We want to be subtracting the 1. So if I subtract 1 from both sides, then I'm going to get sine squared x plus cosine squared x minus 1 equals 0. This is the only part that I want so that it matches. So what I can do is subtract the sine squared x over to the other side. So now cosine squared x minus 1 would equal negative sine squared x. So all of this stuff right here is a negative sine squared x. And remember, we're multiplying these two things together. So now if I multiply those together, I'll get a negative sine to the third x. And that would be simplified. This one, I've got 3 terms. So I'm going to approach this like a quadratic. I'm going to factor this like a quadratic. Okay, when you have a trinomial, you can factor it kind of like how we're used to factoring. So I need 2 things that are going to go here and here. That would make a sine to the 4th x. That would be a sine squared x and another sine squared x. And then I need 2 things that multiply to a 1. Well, those could either both be positive ones or they could both be negative ones. My middle term needs to be a negative, so I'm thinking both of those should be negative ones. To double check, you could actually FOIL. So those would make a sine to the 4th. My outside 2 would be a negative sine squared. My inside 2 would be another negative sine squared. And my outside 2 would be a positive 1. And these middle terms combine to give you negative 2 sine squared x's. So this is what the original was. Okay. So that was just some extra side work. I don't really need that though for my simplifying, so I'm going to get rid of that. Because we're still simplifying the black stuff. I was just showing you why this actually was the correct factorization. Okay, so now, oops, I wanted black. Okay, these are both dealing with that first Pythagorean identity, sine squared x plus cosine squared x equals 1. I want them to look like sine squared x minus 1. So if I subtract 1 from both sides, that's what I'll get. Here's the sine squared x and here's the minus 1. So I just need to get rid of this cosine squared. So I can subtract the cosine squared over to the other side. So sine squared x minus 1 would equal negative cosine squared x. So I can replace this with a negative cosine squared x. And I can replace that also with a negative cosine squared x. And we're multiplying. A negative times a negative turns positive, and then squared times another squared would be to the fourth. So that's how that one would simplify. Okay, now we're going to get into verifying. I personally like verifying better because I know what the answer should be. With all those simplifying problems, sometimes it's a little hard to tell if you're done simplifying, but with verifying, I know my answer. And remember, we only work on one side, and we usually start on the more complicated looking side. So I'm going to start on the left. Okay, so one of my suggestions was it's sometimes helpful to change things into sines and cosines. So, for example, the secant I could change into 1 over cosine theta. And I'm going to rewrite everything else. And when I change that, now we see, oh, those would cancel. So I would be left with a 1 minus cosine squared theta. And if we remember our Pythagorean identities, if I subtract cosine squared theta from both sides, sine squared theta is the same thing as 1 minus cosine squared theta. That's what I currently have. So all of this is just the same thing as sine squared theta. It's a Pythagorean identity just rearranged. And that's what I was trying to show the whole time, so I know I'm done. Okay, with this one, again, visually, whenever I see something squared and a 1, my brain jumps to the Pythagorean identities. And the Pythagorean identity that's dealing with tangent squared looks like this. It's tangent squared theta plus 1 equals secant squared theta. Well, that's what I have. I have tangent squared x plus 1. So all of that is just the same thing as secant squared x. And I'm multiplying by cosine x. Well, secant squared x could be written as 1 over cosine squared x. And I'm multiplying, so technically on the top I have cosine, oops, and on the bottom I have cosine squared. Now I can cancel 1 from the top and 1 from the bottom. If it helps you to write it out, the fact that there's cosine times cosine on the bottom, I can cancel 1 from the top and 1 from the bottom. Now there's technically a 1 on top, and there's still a cosine on the bottom. And that can be written as secant x, and that's what I was trying to show that whole time. So I know I'm done. Okay, with this one, it looks like I've got Pythagorean identities again. Anytime I see something squared and a 1, my brain wants to think Pythagorean identities. That one is the exact same as the last problem. Remember how the Pythagorean identity that we used was tangent squared theta plus 1 equals secant squared theta? So I'm going to replace all of this with just a secant squared theta. And then this one is using the first Pythagorean identity, which is sine squared theta plus cosine squared theta equals 1. And so if I want to subtract 1 from cosine squared, it would look like this, but that's the only part I want, so I'm going to have to subtract the sine squared theta over to the other side. So that means that cosine squared theta minus 1 is the same thing as a negative sine squared theta. So all of this I'm going to replace with a negative sine squared theta. And I have to remember that I am multiplying these together. So let's see, what else can we do? Well, secant squared theta, I could write that as 1 over cosine squared theta if I wanted to. And remember, we're multiplying. So I could write that negative sine squared theta on the top and the cosine squared theta on the bottom. Because remember, technically that would be over 1. And we know that sine over cosine is tangent. So sine squared over cosine squared would be tangent squared. But then I also have that negative sign out in front. And that's what I was trying to show the whole time. So I know I'm done. All right, this one is a little bit more tricky. When I'm looking at the bottom, I really, really wish that it was 1 minus sine squared theta, because that would be a Pythagorean identity. And 1 minus sine squared theta would equal cosine squared theta. But that's not what I have here. I don't have a sine. So I'm going to be tricky, and I'm going to force it to look like this. This is where multiplying by the conjugate helps. So this is a little trick I use whenever the denominator almost looks like a Pythagorean identity, but it's not. So what I'm going to do is I'm going to multiply the top and the bottom by the complex conjugate, or the conjugate, which would be 1 plus, oops, let me fix that. It would be 1 plus sine theta, and I'm going to do that on top and bottom. So now I'm going to rewrite this. On the top, I would have 1 plus sine theta times cosine theta. On the bottom, if I FOIL these two, it's difference of squares because they look identical except one's a plus and one's a minus. So difference of squares, I really only need to do the first two, which would be a 1, and the last two, which would be a negative sine squared theta. Well, that's what I wanted all along, because 1 minus sine squared theta is equal to cosine squared theta. Remember your Pythagorean identity? So if I subtract sine squared theta from both sides, cosine squared theta is the same thing as 1 minus sine squared theta. So on the top, I'm just going to rewrite what I had. But now on the bottom, all of that equals cosine squared theta. Now I have a cosine on the top that I can cancel with 1 from the bottom. So on the top, I'll have 1 plus sine theta, and on the bottom, I'll just have a cosine theta. Now, if we're looking at where we're trying to get to, we're trying to get a secant and a tangent. So sometimes when I know what the answer is, I can kind of work backwards, and I can say, oh, well, what if I split this fraction up? And I write it as 1 over cosine plus sine over cosine. Remember, whatever your denominator is, that has to be your common denominator. And 1 over cosine is secant, and sine over cosine is tangent. And that's what I was trying to get the whole time, so I know I'm done. Okay, this one is a little bit weird looking because of the x's and the y's. We haven't had two different variables. The beginning of the problem is one term, but in the end I have to have two terms. So I'm thinking, let's split the fraction up. So if I split the fraction up, again, whatever my denominator is, that would be my common denominator. So each fraction gets that same denominator of tangent x, cotangent y. And look, I can cancel the tangent x's, so I would be left with 1 over cotangent y. And over here, I can cancel the cotangent y's, so I'll be left with 1 over tangent x. And 1 over cotangent is the same thing as tangent. And 1 over tangent is the same thing as cotangent. And that's what I was trying to show. So I'm done. This one, we're verifying. So the more complicated side is the right side, so I'll start over there. I'm seeing two terms, and both of those terms have a tangent squared. So let's factor out a tangent squared and see what that does. So I would be left with a secant squared minus 1. And that looks like a Pythagorean identity. The Pythagorean identity that deals with secant squared looks like this. Tangent squared plus 1 equals secant squared. So all I have to do to get it to match what we have up here is to subtract the 1. So tangent squared is the same thing as secant squared minus 1. So all of this can get replaced with a tangent squared. And remember, we're multiplying, and that other tangent squared is still out in front. And when you multiply those together, you're going to get tangent to the 4th. And that's what we were trying to show. So we're done with that one. Okay, so verifying is a little easier because you're given the answer. You just have to show all the steps. Simplifying, you just go until it looks as simplified as possible. All right, so now you should be able to do the 5.1, 5.2 assignment. Have a good day. See you after Christmas break. Have a very Merry Christmas.